Welcome. Today we're going to talk about the mean value and min-max properties of the Laplace equation. So again, the goal here is to establish two important qualitative properties. You could call them quantitative as well, but I'm gonna call them qualitative, even though they have a precise mathematical expressions. They're qualitative in the sense that they qualitative properties of U if U is the solution to a Laplace equation equal to 0. Okay, so what do I mean by qualitative properties? We already know one of the properties. One property, well, sorry, I should say we already know one nice qualitative property. I'll put that in an asterisk, which is the zero net flux. So that property is that because if I take some, this is the divergence of U over some area in some set, we'll call it D. Could be like something inside of our bigger set, so this is D. And then of course we know that that's equal to the flux by the divergence theorem over the boundary set. Of the gradient, which we think of as the flux of the heat flux through the boundary, dotted with the normal ds. Okay, so we can do that in 3D as well. So we already know that property, and we know, but because this is equal to 0, that we have 0 flux. Okay, so that's the zero net flux. But now we're going to talk about two more properties, and one of these properties which is called the mean value property. So the mean value property states that on a disk, the average value of U. So on the disk, of course, we always set it equal to f of theta, right? Some boundary condition. Is equal to the value of U at the center of the disk. This is an amazing property, right? So what we're saying then is the average value. So how do we express an average value of f along the whole outer edge of the disk? So let's think about this. Let's draw a picture. So I'm going to draw our disk kind of that way. And again, I think of here's the outer boundary, which we're saying is equal to some function that's given. It's a boundary condition to the problem, f of theta. All right, and then we solve for U, and we find out it's some surface that fills out all the interior space inward from that boundary condition. Like so. All right, so that's U. All right, and now what we're saying is if I take the average value of all of the values on the outer edge, the average of that outer edge will always equal the value of U at the center. So we can express that mathematically as, okay, here's the center, and that's going to be R is equal to 0, right? We're saying that it has to equal the average value of the outer edge, which is going to be 1 over 2 pi, 0 to 2 pi, f of theta, d theta. Okay? So this is an exact mathematical expression, but I like to think of it as a qualitative property because it can be stated in words really simply, and it gives you some idea. Again, and this idea then is and this leads to the second idea, which is that min-max concept, which is which is maybe a corollary of this mean value property, and that's that extreme values, I should say all extreme values of u are on the boundary. Okay, so we'll get to that in a second, but and what we're saying then, of course, is if we have extreme values on the boundary, because u is always the average, it should always be somewhere in the middle. It cannot be a maximum in and of itself, because an average by definition is in between extreme values. Okay, so we'll expand on number 2 in a second, but let's just write down. So this idea, r is equal to 0 of theta is equal to 1 over 2 pi, the average value of the outer edge, d theta, from 0 to 2 pi. So the question is why? And the proof is pretty simple in that we already have the solution. U. And u, of course, is equal to u to r of theta. So we're going to take a disk and we're going to say the radius is r. Okay. For that disk radius r, we have the following: that all solutions are the form a0 plus the sum n equals 1 to infinity of an r n cosine n theta and bn rn sine n theta. Okay, so if that's the solution, it's pretty clear that u, if I put r is equal to 0 of theta, that all of this stuff goes away. That's just 0, and we just get a0. So that has to be the value at the center. All right, so why is it equal to the average? Well, we just compute the average. Let's do that. So if I integrate 1 over 2 pi, 1 over 2 pi of a0, 0 to 2 pi, plus the sum of all that stuff. All right, and this is, of course, a 2 pi periodic. And it's also mean 0. All right, so sines and cosines, half the time they're above the half the time they're positive, and half the time they're negative. Right? So when we take the integral, the area under the curve that's positive and the area under the curve that's negative is always going to balance out. So here is our average. And we see that so all of this goes away, and we're left with the average value is equal to a0, which is, of course, equal to what it is at the center. So there we go. There's a simple example of how this works. It's a very direct computation. Okay, so the next thing we do, of course, is I just want to firm up this last one. So the fact that extreme values of u only occur on the boundary. So this is actually true for any set. So if we have a simply connected set, we'll call it E, right? And I have some boundary partial of E, which we'll call it. What I'm saying is where boundary condition is given, what I'm saying then is that U has a maximum, U's max and min are on the boundary. Okay, So how do we establish this? Well, what we do is by contradiction. Okay, so assume there's some point, there exists a point P right there, maybe inside, that takes a maximum value. It could also take the minimum value. We simply have to change the wording and to do the minimum case. But we'll just do the maximum case, and the minimum case we get for free. If it takes the maximum value on P on the interior, I said interior there. So P is in the center here. It's not on the edge, okay? Well, what we can do then, of course, is put a disk around it. We'll call that disk D. And because we know U, we know the solution, then we already have prescribed a boundary condition on that boundary, right? So we have a partial, an edge to this disk. We already know that the disk D has known boundary condition on the edge of the disk, right? So, of course, we know the mean value property is that the average of U on the outer disk has to equal U at the point P, right? But if it's the average value, of course, it can't be an extreme value. It has to be somewhere in between whatever was between the largest and smallest values on partial. So this is impossible. Except if U is constant. But that's a silly case. We don't have to really consider that. So it's impossible in every non-trivial case. So it must be that, so U, it does actually take the maximum on the partial of E, okay, the boundary of E. So of course we can do the same argument again for the min. We simply replace the statement of maximum with minimum, and we get that side too. So okay, we have this really neat property, and of course this makes sense, just like we thought before, or we showed before. If we have extreme temperatures, let's say on the boundary of some disk or some shape, we expect heat flux to sort of average out those extreme values as they mix, as the temperatures mix and blend with each other on the interior. So we always expect that the extreme values set by a boundary condition will get smoothed out and somehow averaged to some intermediate temperatures in the interior of our sets. Okay, so that's the take-home notion, and that's what I would call the intuitive argument for why that's true. So thanks very much.